Hello, Honors Chemistry, and welcome to Lecture 2 of our Summer Math Refresher, where we're going to talk about scientific notation. So I know you've already learned scientific notation, but it may have been a minute since you used it. So we're going to talk about how to put things into scientific notation and take things out of scientific notation, right? So first of all, why scientific notation, right? We talked in the previous lecture about the concept of measurements, right? But some measurements have lots of zeros, right? So if we look here, radius of an atom, right? This number is teeny tiny, right? And for tiny numbers that have a lot of zeros at the front end, it is ridiculous to write out that many zeros every time, right? Not to mention, by writing out that many zeros, you are quite likely to typo somewhere and get a lot of things wrong just because of attention to detail, right? Likewise, if things are really, really big, like radius of the Earth, right? Again, lots of zeros. That means room for errors just from not writing the right number of zeros, right? So there must be a more convenient way to express these numbers, especially given that we're probably going to have to do math with numbers that are like this, either very, very small or very, very large, right? And scientific notation is just an easier way to express them, especially if we have to do further manipulation, right? So let's talk about how to do that, right? So first, let's talk about our tiny number, right? What that means is what we have to do is we have to put the decimal here, right? That's where we need the decimal to be. Remember that when we write scientific notation, right, the first part of the scientific notation should be a number that is greater than 1 but less than 10, right? This is where we want that number to be, and then we would say it's times 10 to the some exponent, and that's the number of places that we move our decimal, right? So let's go ahead and practice, right? So we need our decimal to be here. It's currently right here. So it's going to have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we would say 2.16 times 10. And then we have to think, well, are we moving 10 places bigger or 10 places smaller, right? I know that some of you guys try, I think in middle school, to memorize something about left and right or whatever. But what I prefer, right, is just let's use reason, right? If it's a tiny number, this is a tiny number, then it should be a negative exponent, right? A tiny number should always have a negative exponent because negative means we are moving the decimal in the smaller direction, right? So this is 10 to the negative 10 meters, 2.16 times 10 to the negative 10, right? On the flip side, right, here, we need the decimal to be here. And currently, it's here. So let's count how many spaces that is, right? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 6.371 times 10 to the, in this case, positive 9, because we need it to move 9 places bigger. So we should always have positive exponents for very large numbers, yes, right? So that's how we reason through that, right? Negative exponent means tiny number less than 1, right? That's what that means. That my number value is less than 1, right? That's how small it is. Numbers that have positive exponents are something far, far greater than 1. All right, now let's go in the other direction. Let's say we have some scientific notation and we would like to translate it out of scientific notation, right? So same principle, right? We're going to start with our exponent. That's a positive 8, right? So what that means is we're going to start here and we're going to go 8 places bigger, right? So 1, and then I'm going to go, well, this is 1, 2, 3. It's right here right now. So 1, 2, 3, 4, 5, 6, 7, 8. 8 places bigger. And I would fill all of these in with zeros, right? And that is our actual number, right? And then we would go ahead and erase all this stuff. And that's our answer, right? Here, this says negative 12, right? Negative 12 from here. So that means, again, negative means smaller. So we're going to go 12 places smaller. So we have 5.33 grams, right? And we got to go 12 places smaller. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we would fill those in with zeros. And that is that answer. So here again, just like in the previous one, you will pause, work them all, and then check them, right? Or I might recommend you just do one set of them, right? So going in one direction and then maybe check them, depending on your confidence level with scientific notation, right? So here we're going to take each of these numbers and turn these into scientific notation, and here we're going to take them out of scientific notation, and we're going to maintain the number of digits, right? The number of non-zero digits. And again, we'll clean up the language on that as we jump into the school year later. All right, so pause, work them, and check them. Okay, so 122. So what that means is the decimal is here currently. We need it to be here. So that's 1.22, right? And it is 2 times 10 to the second positive exponent because it is big, right? Bigger than 1, right? As in this number value is bigger than 1, right? Same thing here, right? So the decimal is currently here. I need it to be here, right? So this is going to be 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Times 10 to the 9th. Positive 9, because this is expressing a large number greater than 1, right? Here we've got 5.5, right? So we need the decimal to be here. It's currently here, so we got to move it 1, 2, 3 places. But it's going to be a -3 because this is a small number less than 1, right? So it should be a negative exponent, right? 0.91, we know that it'll be 9.1. Decimal needs to be there. It's currently here. It needs to move 1 place, so times 10 to the -1. Here we have 2.3 times 10 to something, right? We need the decimal to be here. It's currently here. 1, 2, 3, 4, 5, 6, 7, 8, 9. -9. Yes? All right. Let's go in the other direction. So, 3.5 times 10 to the -5. Negative exponent says we're going to go 5 places smaller. So, 3.5, and then we'll go 1, 2, 3, 4, 5. And that is my actual number, right? 2 times 10 to the +2. So that means 2, and I will move my decimal 2 places bigger, right? And 200 is the number we're actually talking about. 6.022 times 10 to the +23, right? So that would be 6. And then 0.022, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3. Okay, and so if you take a look at that, that is a ridiculous number of zeros. I don't even know that I drew the right number of lumps there. I'm not going to finish that, but it's a boatload of zeros, right? And this is an actual number that we are going to use repeatedly during the course of the school year, right? And that's ridiculous. We can't be writing that many zeros. Ridiculous, right? Which is why we use scientific notation, right? But you should understand the magnitude of that, right? This is how many zeros we're talking about, right? That is a ginormous number. So yeah, bear that in mind. But anyway, it would have a lot of zeros. 9 times 10 to the -12th, right? Same principle, right? -12 means 12 places smaller. So if I have the number 9 with a decimal here, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And all of these spots would become zeros. And again, that's a conversion. That's a conversion that you guys will do, right? Well, we'll use numbers like 10 to the -12th, right? And we're not going to write out all the zeros, right? Here, if we have 2 times 10 to the -2, 2, -2 means here, yes? All right, so again, we need to be able to put numbers into scientific notation, take them out of scientific notation. We need to understand that positive exponents mean large numbers greater than 1, right? And negative exponents mean small numbers less than 1. All right, thank you for listening. Be good and stay tuned for Lecture 3.